This is lesson 76. We will begin this lesson by developing the formula for a new integration technique called integration by parts. Integration by parts is based on the product rule of functions. So we're going to start by letting f to represent f of x and g to represent g of x. In the first step, we will write out the product rule for the composite function of f times g prime of x. So here we go. We know that the product rule will be f prime. We know the product rule will be f prime g plus f g prime. We're going to integrate both sides of this function. Integral of f prime g dx plus the integral of f g prime dx. When I simplify this, I know that there isn't much that I can do on the left side. But if you recall the relationship between a derivative and its integral, the right side will become simply f times g of x. Okay? So let me write it in this form. The next step that I'm going to do is to isolate the integral of f g prime, which gives me f times g minus the integral of f prime g dx. Plus c, if you will, okay? And plus c, if you will, on here. The reason why I didn't really include that constant of integration here is that I know because I'm still integrating another part of this function, that means I can combine the integration constant later on, okay? So now if I set u to be f of x, and dv to be g prime x dx. Then what is du? Well, du is simply f prime of x. And v is going to be the integral of this line here. Okay? So the integral of g prime is g of x. What does this mean if I substitute these relationships back into the previous step? On the left side, I have the integral of f. So integral of f now is u. G prime d of x is dv equals f is u, g is v, minus the integral of f prime. Well, f prime dx is du, and g is v. And this is the formula for integration by parts. Integration by parts is a technique that is very helpful when usually we see a product of two function types in a given function that we need to integrate. And what it does is it allows you to switch which part, so to speak, is easier to integrate. Because you notice that on the left side of this formula, you have the integral of u dv. But then on the right side of this formula, you have the integral of v du. Okay? With experience, you will know how to choose your u and dv effectively to make your work easier. Let's start by looking at example 1. Here we're going to integrate x times e to the power of x dx. Okay? So, what would you choose to let u to be? And what would you choose to let dv to be? Since it's the first time doing this kind of question, I'm just going to go in order, okay? So I'm going to let u to be x. I'm going to let dv to be e to the power of x dx. In the substitution, I know that I also need du. So let's take the derivative of this part. Derivative of x is 1 dx. Okay. And I also need v. So that means I should integrate the second relation here. And here we have v equals to the integral of e to the x is still e to the x plus c, you can say, but we can leave it out for now. Okay. So with these values or these expressions, our formula for integration by parts sets uv. So u is x times v is e to the x minus the integral of v ex du, which is now dx. Okay. It seems doable. So let's continue. X times e to the x minus the integral of e to the x is e to the x plus c. And that's it. This is your very first integration by parts question. B. Here we have the integral of x times sine 2x dx. Let's go from left to right. If it doesn't work, then we'll switch. Okay. I'm going to let u to be x and let dv to be sine 2x dx. du is dx. Integrating the second expression, I get v equals integral of sine 2x. So let me write this down. Integral of sine 2x involves negative cosine 2x, but then I have a 2x here, so that must be over 2. Okay. What does this give me as uv minus integral v du? U is x times v, so it's negative cos 2x over 2 minus v du. Okay, so here we have the integral of negative, so I'm going to make this plus cosine 2x over 2 du is dx, just like that. I think this is doable, so let's continue. I have negative x cos 2x over 2 plus, now I'm going to take the integral of cosine 2x dx and then divide it by 2. Okay, I know that the integral of cos 2x involves sine 2x over 2, but combining with that over 2 that we had already, this is what we have, right? If you're picky, what you can do is you can factor negative 1 over 4. And then here you have 2x cos 2x minus sine 2x plus c. Here is question C. I would like you to take a moment to think about or to try which substitution you will do. You can unpause the video once you're done. Okay, what do you think? It turns out this substitution, u equals to ln x and dv equals to x dx, gave me an easier time. Okay, so du is the derivative of ln x, 1 over x dx, and v would be x squared over 2. Applying the formula of integration by parts, uv, I have x squared ln x over 2 minus the integral of v du, which is x squared over 2 times 1 over x dx. So now I'm going to simplify the second integral here. And I have x dx. That's good news, right? Because this will give me negative 1 over 2 x squared over 2 plus c. If you prefer, you can factor or you can leave it in expanded form and write your answer as such. X squared ln x over 2 minus x squared over 4 plus c. Let's move to some slightly more advanced examples in number 2. Here we have the integral of x plus 2 times 3 to the power of x plus 2 dx. What are your substitution going to be? I will use the following. Let u to be x plus 2, and then dv to be 3 to the power of x plus 2 dx. du turns out to be dx. V is going to be 3 to the power of x plus 2 over ln 3. You can find this formula in the formula booklet if you don't remember it. And so we will have uv, which is u is x plus 2 times 3x plus 2 as an exponent over ln 3 minus the integral of v du. So v is 3 to the power of x plus 2 over ln 3, which is just a number. Du is dx like that. Okay. This allows me to perhaps factor out the 1 over ln 3 because it looks really, really complicated. And then here I have x plus 2 times 3 to the power of x plus 2. Okay. And then minus the integral of 3 to the power of x plus 2 dx, which really is just 3 to the power of x plus 2 over ln 3 again, right? Because we've done it on the side already, plus c. All right. Now I also see that 3 to the power of x plus 2 is a common factor. So let me write this out properly. 3 to the power of x plus 2 over ln 3 multiplied by x plus 2 minus 1 over ln 3 plus c. You can leave your answer like that. Example B. We're going to integrate x to the power of 5 cosine x cubed dx. Here we notice that the cosine angle is x cubed. It doesn't match with x to the power of 5. It may be a good idea to split up the power of 5 into x squared times x cubed, and then cosine x cubed for the angles to match. That could be a strategy, okay? I'm going to let u to be x cubed, and then the rest of that original function as dv. So x squared cosine x cubed dx. Let's see what happens. Differentiating u, du 3x squared dx. I can also write du over 3 as x squared dx. Okay. For the v part, you know how nice now it is to see that you have u squared and dx that matches with du by over 3. Why is this useful? Well, this is useful because this allows me to rewrite dv as the following, as cosine. Well, x cubed can be written as u, and then the rest of it is du over 3, or like 1/3 cos u du, which is much easier to integrate, right? This will give me v equals to 1 over 3 integral of cosine is sine u. But v is 1 over 3 sine. Well, u, I can now write it as x cubed. Now we can go back to apply the integration by parts formula. U times v. Now I have x cubed times 1/3 sine x cubed minus the integral of v du. v du is 3x squared, dx is du, times 1/3 sine x cubed. Okay, so I'm going to do this. Simplify the 3's here. You can cross that out. Let's write this out and see what we have. Minus the integral of x squared times sine x cubed dx. Do you notice any similarities between what you wrote down and what you have done on the side? We saw that if we integrate x squared cos x cubed dx, then we get 1 over 3 sine x cubed. So now if I change that sine x cubed into cosine x cubed here, we can actually deal with this result very similarly to what we got over there. Just noticing how, the integral of a cos and the integral of a sine has opposite signs. And then we can say that our final answer is x cubed over 3 sine x cubed, okay, and then plus 1 over 3. Instead of sine, we have cos, x cubed plus c. You may want to put a star beside this question. Moving on. When we deal with definite integrals using integration by parts, the substitution of your lower bound and upper bound applies to both the u times v section and also to the integration section. All right. So let's take a look. Example 3, evaluate the integral of x cubed ln x dx from 1 to 2. Notice how the advantage of letting ln x to be u is that when you differentiate this, you get 1 over x dx. So it kind of turns back into, 1 over x that can be combined with any polynomial function to simplify it. And then I'm going to let dv to be x cubed dx, so that v is x to the power 4 over 4. And now uv is x to the power 4 over 4 times ln x. We evaluate this from 1 to 2 minus the integral from 1 to 2 of v du. So v is x to the 4 over 4. du is 1 over x dx. So this really is x cubed over 4 dx. Okay, so let's do the substitution first for the first part. So 2 to the power 4, 16 divided by 4 is 4 ln 2 minus 1 over 4 ln 1, which we know that ln 1 is 0. We'll leave it. Minus, here we go. I have x to the power 4 over 4 over 4, so over 16. Evaluate it from 1 to 2. So here I have 4 ln 2 minus 16 over 16 is 1 minus 1 over 16, which gives me 4 ln 2 minus 16 minus 1 is 15. over 16. If you so prefer, you can also write this as ln 16 minus 15 over 16. Okay? But either way is fine. Like leaving it in this form or that form is fine. Good. Now, brace yourself for a super example. Okay? Here, we're going to find the integral of x arc cosine x dx. We would normally think that let u to be x and letting dv to be arc cos x dx would be a good substitution. But if you think twice, do you know how to take the integral of arc cosine x? And if you do, does it help you to simplify your work? Okay. Instead of taking u to be x, I'm going to do it differently this time. Okay. So I'm going to let u to be arc cos x, and I'm going to let dv to be x dx. Okay. Then du, we know it's going to be negative 1 over the square root of 1 minus x squared. Okay. I believe you can find this from your formula booklet. And then on the dv side, I'm going to have v equals x squared over 2. Let's substitute. You will need more room. So I'm going to set it aside here. So integral of x arc cos x dx is equal to uv. So x squared over 2 arc cos x minus the integral of v du. So this is going to be negative x squared over 2 square root 1 minus x squared dx. I left out dx here. Okay. And then you go, well, doesn't that integral look more complicated than what we started with? Well, it depends on how you look at it. Okay. If I try to match up the square root of 1 minus x squared with that negative x squared in the numerator, what I can do is I can do the plus 1 minus 1 trick. Okay. What I will also do is I notice that there is an over 2 in both terms. I will factor 1/2. So I have x squared arc cos x minus, now here we have the integral of 1 minus x squared over the square root of 1 minus x squared dx. Okay, and then plus the integral of 1 over 1 minus x squared dx. So you see how I've split up that term, 1 minus x squared over the common denominator, and then negative 1 over the common denominator. But don't forget to distribute the negative signs carefully. Okay. Why is this useful? If you look at your formula booklet now, what is the result of this integral? That integral turns out to be arc sine. So let me write the first term and then plus arc sine x. Okay. Then I have minus the integral of, simplifying 1 minus x squared over the square root of 1 minus x squared, I have this. Okay. Because I see a radical of 1 minus x squared, you shouldn't be surprised that this relates to another useful integration method called trig substitution. And the pattern 1 minus x squared reminds us that the substitution that we'll use is a sign relationship. Okay, so I'm going to let sine u, to be x over 1, right, using the two terms of the radicand. So x over 1, making the bottom side of the adjacent side 1 minus x squared, the expression that we have in this expression. Okay, so what do we have here? The derivative of sine u is cos u, and du is dx. And 1 minus x squared, this is equal to cosine itself. Cos u is equal to this. Which means I have the following. Arc cos x plus arc sine x minus. Okay, so what do we have here? We have the integral of cosine u. Okay, dx is now cosine u du. Okay, are you with me? And then the question is, how do I integrate cosine squared u? I don't have, a power. This is not really an integration by parts pattern, right? Because it's really just the square of cosine u. So what happens here? What about trig identity? Okay, so we want to relate cosine squared u to some kind of trig identity. What can be helpful? Because we know integrals of simple cosine, sine, tangent, like things like that, right? What about this one? Aha. And so cos u, or cos squared u instead, is going to be cosine of 2u plus 1 over 2. Okay? So we will do another substitution. So before I do that, let me write it out. I have x squared over 2 arc cos x plus arc sine x over 2. And then now minus 1/2, so 1/4, right? The integral of cosine 2u plus 1 du. This is doable. Very doable. Okay, cosine 2u du is sine 2u over 2, but I have that 1 over 4 there. You know what, let's leave it like that for now. Okay, and then the integral of 1 du is u plus c. Okay, keep going. Arc cos x plus arc sine x over 2. Okay. Now I want to simplify my work as much as I can. And what I'm going to do, and I need to still write things back in terms of x, right? Don't forget about that. So 1 over 4, instead of seeing sine to u, I'm actually going to write 2 sine u cos u over 2. Okay, plus u. plus c. This way, I can reduce the 2's. And then we need to go back to the substitution. Oh, I shouldn't be shifting it. So I have sine u. Sine u was x here. And then cosine u is the square root of 1 minus x squared. And then u will be arcsine, right? Arcsine of x. So let's do those substitution. Plus arc sine x over 2 minus 1 over 4. So we said that sine u is x. Cos u is square root of 1 minus x squared. Plus, minus 1 over 4. And u is arc sine of x plus c. And here is our solution.